You told our producers that physical AI is broadly underhyped. What makes this space so hard that most efforts fail when it comes to self-driving cars and self-driving trucks?
In the virtual AI, so the large language models or just models that are running on internet or in our computers, when it makes a mistake, it's annoying, but it's not critical. It doesn't hurt anybody. But in physical AI, mistakes have consequences. You're operating a fleet of robots in a factory. When the robot makes a mistake, the whole line has to be shut down. Same as autonomous trucks. When it makes a mistake, it might collide into a car or a road barrier.
In the world of technology, heroes are everywhere. They're overcoming disruption, delivering sustainable outcomes, and fearlessly forging the future to solve what's next. Join me, Ed McNamara, as we meet the people and businesses driving change in our constantly disruptive world. This is Innovation Heroes, a podcast brought to you by SHI. Everyone's talking about AI that can write code, summarize documents, and answer questions. But there's a quieter revolution happening, one that doesn't just process information, but actually touches the physical world. It's called physical AI. And while a few companies making humanoid robots have grabbed headlines with billion-dollar fundraisers, the broader field remains, in the words of today's guest, underhyped. Why? Because physical AI is hard. When a chatbot makes a mistake, you get a weird sentence. When a self-driving truck makes a mistake, the consequences are far more real. You can't just ship fast and iterate. You have to get it right before anything leaves the warehouse. Today, we're talking with Tete Xiao, the VP of Engineering and AI at Bot Auto. Tete isn't your typical startup executive. He's a computer vision researcher who spent a decade at the frontier of machine perception, including helping create Meta's Segment Anything model, which changed how AI understands images. He's unified robotics frameworks that power how machines learn to move and manipulate objects. And now he's applying all of that to one of the most demanding challenges in AI, making trucks drive themselves safely on Texas highways. For IT leaders who are curious about where AI is headed beyond chatbots and copilots, and what it actually takes to deploy AI systems that interact with the real world, this conversation is for you. Tete, welcome to Innovation Heroes.
Thanks for having me here.
Absolutely. So, Tete, you've spent your career at the cutting edge of computer vision, including work on Meta's Segment Anything model, which was kind of a watershed moment for the field. For listeners who might not be familiar, what did that breakthrough actually change? And what drew you from pure research into the world of autonomous trucks?
About a decade ago, when I started working in computer vision, we really struggled with almost everything. Our models wasn't able to recognize even accurately just cars and people. Nowadays, beginning from the Segment Anything model, computer vision can actually generalize to objects that it has not seen before. It works in the real world. And that's because of the foundation model paradigm. We know that word often from large language models. That is a model that understands everything. It learns from vast amount of data, and it's able to generalize to different kinds of tasks. And that was the same as Segment Anything model. It was the first computer vision foundation model. Had always been a researcher in the bottom of my heart. I started my research career now over a decade ago, starting from 2015. I always enjoyed exploring new ideas and doing cutting edge research. On the other hand, I see how impactful this research works can be if we apply them into the real world applications. Autonomous trucks is very important application of technology. Logistics in America is about $800 billion to $1 trillion industry. And Class 8 trucks is about $500 billion of that. It has tremendous impact on everybody's life. And that's what drew me into the industry.
You told our producers that physical AI is broadly underhyped. What makes this space so hard that most efforts fail when it comes to self-driving cars and self-driving trucks?
In the virtual AI, so the large language models or just models that are running on internet or in our computers, when it makes a mistake, it's just annoying. It gives us a broken sentence or it hallucinates something that never happened before. It's annoying, but it's not critical. It doesn't hurt anybody. But in physical AI, mistakes have consequences. If you are operating a fleet of robots in a factory, when a robot makes a mistake, the whole line has to be shut down. Same as autonomous trucks. When they make a mistake, it might collide into a car or a road barrier, and these are important. So the threshold for deploying this type of technology and the reliability and the safety standards are extremely high in the real world. And this is actually something that is very challenging for deep learning models because these models are able to do a lot of things. So it's not hard actually to make these models do most of the stuff you want to do to some extent. It's kind of doing that, but you also don't really know when it will make a mistake. So it's empirical. And that's why we have to go through a lot of validation and testing to deploy any physical AI in the real world.
You said you don't know when it will make a mistake, but in your case, you don't know where it will make the mistake either, right? I mean, if it's in the somewhat controlled environment of the production line, that's one thing. If it's out there on the road on its own, that's a whole nother ball game, right?
Absolutely. So that's why our system has explicit modules to check when the model's uncertainty is high, and we take actions on that. For example, when we know that the detection range is lower than is shorter than expected, we go into degraded mode. That's the same as human beings. When we are uncertain about the object far away, is like, well, is that an obstacle on the road or not? The first thing we do is always to slow down. And our system explicitly checks all of that. And that's just an example for deploying physical AI. We need to have modules that checks everything that can possibly go wrong and the things that we don't expect to go wrong, but we also have a contingency plan on that. And that applies to all physical AI applications. And that's why it's challenging. But also that's why it's high impact when we do make it work.
You mentioned that when you started in computer vision in 2015, nothing really worked. So I'd love to get your take on like how nothing really worked and like what's changed. Like walk us through the breakthroughs that made today's autonomous systems possible.
So in the past decade, there are a couple of milestones that we achieved collectively as a community. The first one I'd say is the transformer architecture. Now, we hear that architecture all the time for large language models. So it uses a mechanism called attention to process a large chunk of data. For computer vision, like we adopted this architecture as well after, I would say, 2020. We are moving all of our computer vision architectures into this paradigm. And now we are able to fuse information coming from different kinds of sensors. Back in the days, we had to write specific rules on how this information, for example, coming from radar, LiDAR cameras, how a model should weigh with the importance of each modality. And nowadays, we just need a single transformer architecture that acts like a model that learns everything and knows what is important at what time from each of the sensors. So the transformer paradigm is critical. Is critical. And secondly, we now know how to leverage compute. Back in the days, we had tremendous difficulty when we increase the number of parameters in a deep learning model. So these parameters are kind of like the number of neurons in our brains. The intuition is like the more parameters we have, the bigger brain that the AI has, so it gets smarter. We didn't know how to increase the size of the brain because whenever we increase that, we don't have enough data for these brains, and in the end, it just memorizes the testing set. It's like if you only have like 1,000 problems for the final exam, but your brain is really really smart. You just memorize everything. You don't really need to learn the rules and the knowledge beneath it. You just need to memorize the test set. So that's called overfitting. So every time we train a bigger model back in the days, and then we always overfit. And now we know how to leverage data and compute to make these models more powerful. Lastly, that we know how to use data more efficiently instead of just using like kind of a shotgun blast type of strategy where we collect all kinds of data and just throw into the model. And now we know what types of data is more important and what is not. So instead of having to use like millions and trillions of images, we just need to pre-train these models using near net scale data. But after that, we always use specialized data, task-specific data, to improve these models. That's something that's important as well. And we also have other kind of tools such as reinforcement learning, and that's more and more used for computer vision as well.
So I think you're talking about the compute-driven paradigm, and you compared autonomous driving to AlphaGo. What does it mean for a truck to discover driving strategies that humans have never thought of?
Well, let's take a step back and think of like human drivers. Like we only have like two eyes, and we're always looking forward. And sometimes we look at the rearview mirror, but most of the time we're looking forward. That means like our driving strategy is limited by our own hardware, quote unquote, because we it's just our physical embodiment, and our driving strategy sometimes is not the safest way. Imagine like we can track a lot of cars at the same time, like including the cars that behind us or in our blind spot. We can probably drive safer. And before you mentioned the reaction time of human beings, and that's in hundreds of milliseconds. If we don't have to wait until after a few hundred milliseconds, we can react almost instantly to everything that's happening, including like the instant that's in front of us. So we can't just mimic human beings. We want to be better than human beings. We want to be more efficient. We want to be safer than human drivers. And speaking of efficiency, I don't know whether you noticed that before. If you turn on, for example, even just assistant lane keeping and assistant car following, it's actually more fuel efficient than human drivers, because computer knows almost exactly the velocity of the front car and the current car, so it can maneuver in such a subtlety that is efficient. We want computers to discover a better driving strategy on its own rather than just learning from human priors. And that's what I mean by the AlphaGo paradigm. And when you look at Go, for example, we've had these paradigms of how to play Go games since 1,000 years ago. And we have all the knowledge. And indeed, the first version of AlphaGo was trained on these paradigms, was trained on these strategies. But when you just unleash the power on compute of AI and let computer discover the best strategy for that, it's always better than human beings. And I believe driving is the same. And the caveat, though, is that we have the traffic law. We have rules for driving. And on that, we need to adhere to the law 100% of the time. And we have these modules explicitly when we train these AI models, as well as deploying these AI models into the real world. So our truck does not violate traffic laws. And that's, by definition, is in the system.
I always felt that when autonomous driving, when you have control over every vehicle on the road, theoretically, you could get more vehicles, in tighter spaces, because you don't have to leave that reaction time, because you're all going to be reacting at the same time, right? How much trouble are human drivers to your trucks?
I would say most of the trouble and the challenges that we're trying to solve are because of human drivers.
I figured, yeah.
Yeah, if the world is just like robotic drivers, we're actually not that worried about our trucks.
Right.
If everybody follows traffic rules, we'd be fine.
How do you let an AI explore when the stakes are so high? And what I mean is, you can't just let a truck experiment on I-10. How does simulation fit into your safety validation process? And is it something that's ongoing?
Simulation is the cornerstone of our validation pipeline. And for the reason that you just mentioned, we want to explore all kinds of scenarios, including even the corner cases that we believe that doesn't exist in the world. On the other hand, like you'd be surprised at how many cases that we thought wouldn't happen, but actually our trucks saw that happening in the real world. Like, people, we saw pedestrians walking on a highway, for example, I-10 before. And I thought nobody would do that. So, there are many corner cases that we could record in the real world. But even when that is true, like we cannot maneuver our trucks around these people to kind of explore, what kind of consequences would happen if we do X, Y, and Z, because that would be unsafe. So we have only one option left, which is simulation. And actually, simulation is a better strategy for training these AI models and letting AI explore, because you can enumerate all kinds of strategies without having to face a safety issue. Like, yes, you can try to get very close to a pedestrian, and immediately you'll realize that's not a good idea. You can try to speed up when the adjacent lane is extremely slow, and then you'll realize that's not a great idea, because there might be some non-compliant driver that tries to cut in, and you don't have enough time to react to that. Even if you react almost immediately, there's the braking distance is not long enough. So there are all kinds of situations that we cannot experiment with in the real world. So we use simulation for that. And secondly, simulation is extremely fast, because we leverage like NVIDIA GPUs to run computation. So every minute of the simulation time is equivalent to about 1,000 minutes of the real world driving experiences. So a couple hours of simulation time is equivalent to like years and years of driving in a real world. So it's extremely efficient.
And you mentioned different scenarios on the road, like, and there's a famous ethical thought experiment, the trolley problem, about an autonomous vehicle having to choose between two bad outcomes. How do you actually handle those edge cases when you're writing real code for real trucks? Like, how do they make that decision?
Well, philosophically, it's a dilemma. That's why it's an interesting question. There's no right or wrong answer, but practically, I believe there is the right answer, which is we must follow traffic law. When we drive in the real world, sometimes we're negotiating with other road users, so we want to be predictable. We don't want to swerve into a different lane, and then all the other road users will have to react to that. So our behavior should be to brake hard and to avoid any collision and try to stop in the lane instead of going into the adjacent lane. By doing that, I think it's the safest way.
So let's talk about bot auto specifically. You're targeting fuller driver out operations, which means no safety driver, no remote operator, just the truck and the highway. What does truly autonomous mean in practice, and why is it so much harder than having somebody in the back seat?
Truly autonomous means that there's nobody in the cabin, nobody in the driver's seat, nobody in the back seat. And we send the trucks out, and it's supposed to show up on its own at the destination. And the safety critical decisions will have to be made by the truck on its own. And there's no remote assistance, there's no remote driving. And the reason that when someone is actually in the cabin, even when that person is not in a driver's seat, is much easier, because you can always hold the emergency button. We call it internally the big red button. So you can just press the button and the truck will stop in its lane if you feel like anything is going wrong. But in the real operation, like, you can't expect that. So when you have a human being in the cabin, you are basically having a zero latency safety monitor that can stop the truck at any given time. That means like the safety critical decisions doesn't have to be made entirely by the onboard computer. But then when you remove that safety driver, safety monitor, every single critical decision has to be made by the truck. And that's our design principle from day one, because that's the only way towards fully autonomous driving and operation.
Infrastructure is critical for any AI system, operating at scale. Talk about the speeds and feeds a little bit. What does it take to support autonomous trucks? Kind of the compute, the data pipelines, the real-time processing. How does this work both within the truck and on the back end?
Yeah, the magic for pulling this off with such a small team is to have great infrastructure. Without a good infrastructure, even a big team can't do much, let alone a small team. So our pipeline is almost automated for every single step, all the way from the data coming out from the truck. The driver doesn't need to do anything, the safety monitor. Everything is recorded, processed, structurized, and indexed by the computer. After every trip, the data flows off from the truck automatically, going into the storage in the data center. And over there, our offline system processes all the data, delete, the data is kind of boring. And for these interesting data, or the data that might be useful to train a machine learning model or for our validation pipeline, we extract even more information from it, frame by frame, and save them into our database. And later on, when we train the model, these data are already kind of sharded in the system, and we can use them as well. So that's our entire pipeline. And also, when we deploy a model, it's also automated. So every code change the engineering team makes, it triggers our CI/CD pipeline, which pulls the validation data out of the database and run the algorithm again through the entire pipeline to make sure that there's no regression, and to make sure that nobody made any kind of funny mistake that caused any safety issues.
So for IT leaders listening who are deploying AI in their own organizations, maybe it's not autonomous trucking, maybe it's, manufacturing, healthcare, logistics, security, what lessons from your experience would apply to their work in the physical world?
Anything that deploys in the real world requires comprehensive validation, simulation, edge case testing, and safety is one of the most important things in the pipeline. We must focus on that. And there's actually a balance that you can achieve with speed and safety, which is to build better infrastructure and better tool chains for deploying your applications. Sometimes you don't have to slow down for that. You just need to automate the entire pipeline. Imagine if there's a test. When you pass the test, you know that the software doesn't have a problem in this particular aspect. And then every time when you change the software, you just need to run the test. I think the 21st century is really like the time when we sort of rethink everything and digitalize and automate and use machine learning and AI for our workflow. And that's something I've learned from my past experience and also at Bot Auto.
So you were looking ahead already, and what should our listeners be watching for and opportunities that might open up as these technologies mature? Where physical AI is going. If this is your chance to make kind of pie in the sky predictions. Can you even forecast 3 to 5 years from now, or is that even difficult?
I think it's difficult in a way because we don't know precisely what's going to happen in 3 to 5 years. And the reason is that technology is progressing at such a rapid speed. On the other hand, if you zoom even a little bit longer, the prediction becomes easier because we know like something is inevitable.
Right.
Automation is inevitable. We overestimate how much can be achieved within 2 years, but we underestimate how much can be achieved in 5 to 10 years. Physical AI will be broadly available in the next 5 to 10 years, starting from autonomous driving. I believe in the next 2 to 3 years, you will see trucks going all over the place, and there's more and more autonomous trucks. There will be robots more and more robots in factories, not just the industrial robots that are doing one thing. You will see like humanoids walking around the factory floor and doing the work that's many times dangerous for human beings. And they can do 24/7 shifts as well. And then you will see like miners that are robotic miners. In mines, these are traditionally dangerous places. You will see robots in aiding for disaster reliefs to go into tunnels or places where human beings don't want to be. Physical AI will be there. There are a couple of challenges out there for robotic applications, but I believe we will get there. It's inevitable.
I love that you led with the inevitability and then worked backwards. You said it's inevitable, so we know these things are going to happen. It's just hard for us it's easier to predict, that eventually something's going to happen, but 3 to 5 years is more difficult. That's like one of the first times a guest has said that, and I really, really appreciate your honesty like that. That's fantastic. So we've pulled back the curtain on a kind of AI that doesn't get as much attention as chatbots and copilots, but might ultimately be even more transformative. Physical AI is where the rubber meets the road, literally. And the lessons Tete shared today about simulation, safety validation, and being obsessive about getting it right before you deploy, those apply to any organization building AI systems that have real-world consequences. Big thanks to Tete Xiao and the team at BotAuto for giving us a researcher's eyes view of what it actually takes to make autonomous trucking work. It's not just about having the best algorithms. It's about the infrastructure, the validation, and the partnerships that make it possible to move from lab demo to commercial operation. If you're leading IT or digital transformation at your organization, and you're thinking about AI systems that interact with the physical world, or just want to understand where this technology is really headed, let's talk. Visit shi.com/AI to learn more about how we're helping innovators solve what's next. For more episodes of Innovation Heroes, visit shi.com/heroes, and be sure to subscribe wherever you listen or on YouTube. Until next time, keep solving, keep building, keep innovating. Tete Xiao, thank you so much for your time today.
Thank you, Ed.